Hey guys, welcome back. We are starting chapter 5 titled Molecules and Compounds. Okay, so elemental sodium is an extremely reactive metal that dulls almost instantly upon exposure to air. And elemental chlorine, right? We find chlorine in naturally as it's a diatomic, so it's Cl2, two chlorine molecules are bound together. Chlorine is a yellow gas with a pungent odor. It's also highly reactive and poisonous. But the interesting part about this is that we eat sodium and chlorine in the form of table salt. So sodium chloride is a compound formed by sodium and chlorine, and the properties of this compound are drastically different than the properties of the elements that compose it, right? There's nothing too poisonous about salt. We can eat salt and put it on our food every day, right? So it's important for you just really fast to understand that elements that make up compounds have different properties than the compounds themselves. Also, compounds display constant composition, and what do I mean by that? A compound is, first of all, different from a mixture of elements, just like we talked about before. And in a compound, the elements combine in fixed, definite proportions, right? So for every water molecule, there's always 2 hydrogens and 1 oxygen. In a mixture, they can have different proportions whatsoever, right? So mixtures aren't pure substances. Mixtures are a combination of different compounds, okay? And they can have proportions that vary. But within a compound, the proportions are definite and they're fixed. So a mixture is another, this is a balloon right here, is filled with a mixture of hydrogen and oxygen gas. The relative amounts of hydrogen and oxygen are variable, but it's important to know that when we look on a molecular level within the balloon, hydrogen is a diatomic, so it's 2 hydrogen molecules chemically bound together, and then oxygen is also a diatomic, meaning that it has it's always two oxygen molecules chemically bound together. A chemical compound, right? This balloon is filled with water, right? Of molecules composed of this balloon is filled with water composed of molecules that have a fixed ratio of hydrogen to oxygen. Just like I mentioned before, it's always going to be 1 oxygen for every 2 hydrogens, okay? And that's not going to change. If we change that, then it's no longer water, okay? So compounds are always in fixed, definite proportions. So chemical formulas is how we represent compounds, and it's important for you to understand how we read chemical formulas. So compounds have a constant composition with respect to mass because they are composed of atoms in fixed ratios. Okay? A chemical formula indicates that the elements present in a compound and the relative number of atoms of each. So for example, just to make sure this is all review, but again, we have water here just to make sure that you understand. H is the symbol for hydrogen. 2 is the subscript 2 is indicating that there are 2 hydrogens. O is the symbol for oxygen, and because there is no subscript after the O, there's implied a subscript of 1 indicating 1 oxygen atom. So let's look at a little bit more of a complicated compound. This is called magnesium nitrate. This is actually an ionic compound. You don't need to know this just yet, but let's make sure that you understand what's going on here because this one's a little bit more complicated. So first of all, Mg, that's the symbol for magnesium. Because there is no subscript after the magnesium, it's implied that there's just 1 magnesium atom. Okay. Then we have parentheses, and within the parentheses, we have, it's called a nitrate group. We will learn about these polyatomic anions later on, but because it's within parentheses, the NO3 subscript is a group, okay? And within that group, we have one nitrogen atom per group, and we have 3 oxygen atoms per group. We close the parentheses, okay? So that's indicating, again, that that's just the NO3 as a group. The subscript after the parentheses indicates that there are 2 nitrate groups within the compound. So if we wanted to count up all the atoms to make sure that we have it right, so this magnesium nitrate compound, MgNO3 subscript 2, indicates a compound containing 1 magnesium atom and 2 nitrate groups, or NO3 groups. So again, 1 magnesium. If we wanted to count out the nitrogens, there's 1 per group, and there are 2 groups, so 2 nitrogens total. And oxygens, there are 3 oxygens per group, and because there are 2 groups, that's 6 oxygens total. So that is essentially how you read this is in particular an ionic compound, and that's how you're going to read the subscripts and the parentheses and all that good stuff. Okay, so it's important for you to understand how to list in the correct order elements when you're writing compounds. Okay, so there's a set of rules that you have to follow. The first rule is that chemical formulas list the most metallic element first. So we all know that metals are on the left side of the periodic table and nonmetals are on the right. And in compounds that do not include a metal, the more metal-like element is listed first. And what do we mean by metal-like element? You're going to follow the periodic trend for metallic character that we learned from the last set of slides. Among nonmetals, those to the left in the periodic table are more metal-like than those to the right and are normally listed first. And then within a single column in the periodic table, elements toward the bottom are more metal-like than elements toward the top. So, example, water, H2O. So this compound does not include a metal, all right? So we have to list hydrogen first, because hydrogen is on the left side of the periodic table. So it's technically more metal, it has more metallic character than oxygen. So hydrogen is going to go first, and then oxygen. This is an ionic compound that we just went over, all right? This is a magnesium nitrate. So this does include a metal, so we're going to list the metal magnesium first, and then within the nitrate group, within the parentheses, so these are nonmetals, okay? So among the nonmetals, nitrogen is to the left of oxygen. So since nitrogen is to the left of oxygen, we're going to list nitrogen first and then oxygen. And then we have finally another ionic compound with a metal, copper sulfate. So copper is a metal, so we're going to list that metal first. And then the sulfate group, right? SO4 is a sulfate group. You'll learn that later on in this chapter. But sulfur and oxygen are within a single column on the periodic table. So because elements toward the bottom are more metal-like than elements towards the top, sulfur is below oxygen on the periodic table, so sulfur will go first, and then oxygen. Okay, so elements, we're kind of going back to the whole compound element situation from a few lectures ago. Elements may be atomic or molecular. An atomic element is the most basic unit that for mercury, for example, right? It's just liquid mercury. It's just a bunch of mercury atoms floating or hanging out. They're not bound to each other necessarily. They're just all single mercury atoms. So this is an atomic element. The same thing for the metals, sodium, lithium, potassium, all that stuff. Even the same thing as the noble gases, okay? But then we can also have molecular elements. The basic unit that compose chlorine, for example, these are diatomics, right? So they're not made up of multiple elements, but they are two elements chemically bound together, making it a molecular element. So it's important for you to understand the distinction between the two. So all of the diatomics are molecular elements. Most of the metals and the halogen gases are atomic elements. So 7 elements from the form diatomic molecules under normal conditions. Like this is how we find them in nature, right? Again, a molecule, it's the tiniest independent particle of a pure substance. Di means 2, so diatomic, 2 atoms, right? The smallest particle of these elements is 2 atoms that are chemically attached to each other. These are all of the diatomics. You're going to need to memorize these. So most of the time when we're talking about chemical compounds and we're talking about chemical reactions in the future, and I'm say gaseous nitrogen, you always think of N2, unless I specify an atom of nitrogen. Okay. Same thing goes for chlorine, bromine, fluorine, iodine, and hydrogen, and oxygen. And just in case you're wondering, here's where they are on the periodic table. So compounds. So these are not elements, right? These are not molecular elements, and these are not, these are not atomic elements, and these are not molecular elements. These are now, so I'm going through all this again. Now we're going into compounds. Compounds fall into 2 general types. We have molecular, which is on the left. The example is water. And we have ionic, that's on the right, sodium chloride. Molecular compounds are formed from 2 or more non-metals. Okay? So molecular compounds are formed from 2 or more non-metals. Ionic compounds contain 1 or more cations paired with 1 or more anions. So ionic compounds, cations and anions paired together. And in most cases, cations are metals. We've talked about this a bunch already. And anions are nonmetals. So, and the basic unit of an ionic compound is called a formula unit. So a formula unit of sodium chloride would just be Na and Cl. Okay. A molecule of water is H2O. But again, it's important for you to understand molecular compounds, 2 or more nonmetals chemically bound together. Ionic compounds are a metal and a nonmetal, and they form a formula unit. All right, so just a reminder, compounds are formed when electrons between 2 or more elements are completely transferred. So complete electron transfer, that's ionic bonds, or they're shared, that's covalent bonds. We will look at ionic bonds first, but if you just want to take a quick look at this picture that I have on the slide here where we have M is a metal and NM is a nonmetal, and you can see the top left where we have the metal gives an electron to the nonmetal, right? So the arrow is going towards the nonmetal, so that lone electron on the metal is given to the nonmetal, and then we follow down, transfer of electrons. See that arrow? Now metal that lost the electron has a plus charge, and the nonmetal gained an electron, so it has a minus charge, and the electrostatic interaction between the two is an ionic bond. Okay, so it's the electrostatic interaction between a full positive charge and a full negative charge that makes this ionic bond. Covalent bonds are different. Covalent bonds are a bond between 2 nonmetals, right? Where neither one of them is going to give up an electron. So they're like, okay, we'll just share it, right? And then if we follow the arrow down where it has non-metal, non-metal, and see the two dots in between the two nonmetals, that indicates a sharing, and that is a covalent bond. A covalent bond is the sharing of two electrons. So like I said, we're going to look at ionic bonds first. Okay, so nonmetals form anions, right? In order for an ionic bond to form between two elements, one element must have a plus charge and the other must have a minus charge. Ionic bonds are between metals and a nonmetal. So here's my non-metal example is oxygen. Okay, so remember oxygen, 8p, that's 8p plus, that's 8 protons plus 8 electrons, that equals oxygen, right? And its big thing is if when we look at this oxygen, it's charge neutral, meaning there's no charge around it. If there were a charge around it, it would be indicated, okay? The electron configuration for oxygen is 1s2, 2s2, 2p4. And as you can see here, this is the orbital diagram of oxygen, okay? And when an oxygen interacts, remember we're looking at ionic bonds, so it's between a metal and a nonmetal. So when oxygen interacts with a metal, all right, it gains electrons, okay? And it gains two specifically. Why? Well, that's because we want this full valence shell, right? So what we're doing here is we're going to fill the last two half-filled 2p orbitals, right, with 2 electrons. And those are I have to pair them spin down, and that's in red. Okay, so those are 2 electrons because non-metals gain electrons. And oxygen gains 2 because it has space for 2 more electrons. Now it has a full valence shell, right? 8 electrons total. Its electron configuration is 1s2, 2s2, 2p6 now, all right? And that's the plus 2e right here. That's for the 2 red electrons. So that gives us an overall charge of -2 on oxygen. Okay, so it's an anion with a -2 charge. So just remember, if an atom gains an electron, it's called an anion. Metals form cations. Okay, so my metal example is lithium. Whoops, okay. So lithium has electron configuration 1s2, 2s1. It has 3 electrons total. Oops, sorry, none of that came out right. So we're still up here, still at the top, okay? So 3 electrons, 3 protons, that's a charged neutral lithium, okay? And remember, metals give up electrons, they lose electrons. So we have which electron is going to be lost? It's going to be this 1 electron in the 2s orbital. So if we go down to the next line, now the electron configuration is just 1s2, right? It lost that 1 electron in the 2s orbital. And lithium becomes a cation with a +1 charge. It is extremely stable like this because now it has a full valence shell, right? It has a full valence, and its valence is particularly the 1s2, right? So again, if an atom loses an electron, it becomes positive, and it's called a cation. So metals plus nonmetals equals an ionic bond. So again, metals that lose electrons, so lithium lost 1 electron, right? To be lithium plus, right? Because it lost that 1 electron. Nonmetals gain electrons, so oxygen will have gained 2 in order to be oxygen 2 minus, okay? So when lithium and oxygen interact, the lithium will give up its electron to oxygen. Since oxygen needs 2 electrons to fill its valence shell, and lithium only has 1 electron to give, there needs to be 2 lithium atoms to form the neutral ionic compound Li subscript 2O. All right, so you'll notice here I put 2, so now 2 lithium atoms give up 2 electrons, right? Those 2 electrons are the electrons that are going to be given to oxygen. And overall, it's going to form a compound Li subscript 2 O. Okay, so because there are 2 lithium cations for every 1 oxygen anion, right? And that's because lithium has a plus, each lithium has a +1 charge, and each oxygen has a 2- charge. So you're going to need 2 lithiums to balance out that -2 charge on the oxygen, okay? Charges of the cations and anions must equal the charge of the ionic compound, okay? They have to equal the charge. And also note, charge will always be indicated. So for example, this Li2 lithium, we're going to call this lithium oxide, but it's Li subscript 2O. There's no charge indicated anywhere around here, so you need to assume that it's charge neutral. If it's not charge neutral and there is a charge that's indicated, you'll see that later on, okay? But when we're starting to write out ionic compounds, we're going to assume the overall compound is charge neutral, so the plus charges have to equal the minus charges. You cannot change the charge on lithium. Lithium will always be a +1. Oxygen will always be a 2-. All right? So the only thing that you can do when you're writing out ionic compounds is to change the subscript of either the cation or the anion, right? I changed the subscript to 2 to show there has to be an overall +2 charge to cancel out the 2- charge. So here's just another pictorial example, right, of another would-be cation, right? Sodium, it's a metal, so it's going to give up an electron. Which electron is it going to give up? It's going to be that 1 electron in the 1, 2, N equals 3 shell, so it's the 3s1 electron. It's going to give that up, right, to become a positive cation. It's going to have an overall +1 charge, and it has a full valence. Oops, sorry about that. Let's skip forward. We can also look at an anion, right? Right now we're looking at fluorine. It's a non-metal, okay? It has 1s2, 2s2, 2p5 electron configuration, and it has a spot open. It needs 1 more electron to complete its valence shell. So when it gets its electron back, or gets an electron from a metal, right, it's going to be a negatively charged cation, and since it gained 1 electron, it's going to have a -1 charge. So when we basically put these 2 cation and anion, or metal and non-metal together, that electrostatic interaction between the positively charged cation and the negatively charged anion are going to attract, and they're going to basically be held together in an ionic bond. You might wonder, well, wait a second, how did fluorine get that negative? Well, in reality, what would happen is that neutral fluorine would react with a neutral sodium atom. The electron transfer would happen when they interact, and then they'll stay together after the interaction, after the electron transfer, and they will stay together because of the resulting ionic bond. Okay, so again, what makes fluorine gain electrons and sodium lose electrons? It all depends on where they are on the periodic table, and this is basically all of the Chapter 9 lecture that I went over on Tuesday. So again, atoms may lose, gain, or share electrons in order to get to a more stable valence electron configuration. This is essentially chemistry, right? A configuration with the S and P sublevels filled is incredibly stable. That's essentially what every atom wants to get to, is a filled valence. Now, whether they lose or gain electrons in order to get a full valence, that varies on whether or not it's a metal or a non-metal, but this filled S and P sublevels or filled valence is a really important rule called an octet rule. And the reason why it's called an octet rule is because S orbitals can only have 2 electrons. P orbitals can have 6. So when they're filled, which is a full valence, 2 plus 6 equals 8. So this is the octet rule, all right? So let's look at krypton, for example. Okay, krypton, here is the electron configuration, and then here is the orbital diagram for krypton. I have the highlighted or electrons in red. Those are the valence electrons, okay? Krypton is a noble gas. So it has a complete valence. This is why krypton doesn't react with anything. It's because it doesn't need any electrons to have a full valence, and it doesn't need to give any away. It's complete, so it's happy, okay? Again, this is the filled valence shell. Let me take a look at that. So again, these are filled valence shells, even though we fill the 3D after the 4s, right? And then the 6p, the valence shell is the shell with the highest principal quantum number. Argon is another example. That's a noble gas. Here is its electron configuration, and you can see here that it has a full valence, right? The 3s and the 3p are filled, totaling 8 electrons. All right. Neon, here's the electron configuration, and again, fill valence shell, total 8 electrons. So every single element is trying to get to this filled valence shell, okay? Whether it's gaining electrons or giving them away. And helium is one example, the only exception to the octet rule. It has a filled valence, but its valence is only 2 electrons. Okay, that's because helium exists only in the n equals 2 energy level, so it only has 1 s orbitals, and since it only has an s orbital, it can only have 2 electrons. Okay, so something like hydrogen, lithium, beryllium, right? Those guys are happy with 2 electrons because they are the closest to helium on the periodic table. All right, so hydrogen does not obey the octet rule. It still obeys a full valence shell rule, but its full valence is 2 electrons. Helium, same way. Lithium, that's why lithium likes to lose 1 electron to get to a 1s2 electron configuration. Beryllium, same way. So all of these guys are exceptions to the octet rule, and that is because helium's filled valence is 1s2. So again, considering the fact of all of these, remember, the noble gases are on the far right side of the periodic table, okay? And I just went through the electron configurations for those. So basically everybody else is trying to get to that point. They're trying to get to that full valence. So you can predict what the charge of the main group atoms will be on, or elements will be, by where they are on the periodic table. This is why the the alkaline metals, okay, so it will just like the first row, oh my gosh, I can't talk, sorry about that. The first column metals, all right, the alkaline metals, those guys will always be +1 because all they have to do is lose 1 electron to get to their stable noble gas core, right? Potassium will always lose 1 electron to have a noble gas configuration of argon. Sodium will always lose 1 electron to get to a stable noble gas configuration of neon. Beryllium, magnesium, calcium, those guys will always lose 2 because it's easier to lose 2 than to gain 6. Remember, because we're trying to get to a full octet. And then we have nitrogen. Nitrogen likes to be a -3 because all it needs to do is gain 3 electrons to have a noble gas configuration, that of neon, phosphorus, that of argon, arsenic of krypton, right? Oxygen will always gain 2 to get to neon. Sulfur will always gain 2. And then the halogens will always gain 1 electron to get to its neighbor noble gas configuration. Okay, so we can predict the charge of these ions exactly where they are on the periodic table. So again, ionic bonds, opposite charges attract. Okay, and the ionic bond, or the electrostatic interaction that is the result of a complete electron transfer from a metal to a nonmetal, results in an ionic bond. Okay. Compounds held together by ionic bonds are called ionic compounds. The plus charge and the minus charge of ions must balance. They must equal 0. So this is why magnesium chloride, right, is MgCl2. Magnesium is always a +2 cation because of what we saw here. Magnesium is always a +2 cation, and chlorine is always a -1 anion. So in order for those to balance out, you have to have 2 chlorines, right? The common name for an ionic compound is called a salt. Again, it's a metal and a nonmetal. And many ionic compounds are comprised of this thing called polyatomic ions. You'll see this NaNO3, all right? Na, sodium. The polyatomic anion that we're looking at is the NO3. We will talk about that later. Okay. So metal ions, some metals have fixed charges. We already know group 1A and group 2A have fixed charges. Some do not. Okay, so metal ions from group 1A, 2A, or 3A, right, have only one possible charge. +1 for group 1A, +2 for 2A, and +3 for 3A. Some other metals with some other metals with only one possible charge are, we have silver +1, zinc +2, and cadmium is also a +2. These metals do not have any specific naming rules. Okay, so when we start naming ions, sodium cation is simply called a sodium ion or sodium cation, but you have to leave off the word ion or cation when you are naming compounds. And you'll see this a lot later, okay? So when we're talking about them individually, we can say the sodium ion or the sodium cation, but when we're talking about them in terms of a compound, we're going to drop the anion and cation, and we're just going to say, and we're also going to drop the ion, and we're just going to say sodium. Oops, sorry, let me go back here. The other thing I want you to notice too is the transition metals. You can see here I have the charges listed. Gold, mercury, cadmium and mercury and zinc all have one charge, but gold, mercury, and all the first row transition metals can vary. All right, so titanium has several different charges. Iron, cobalt, nickel, all of those guys have several different charges. So we'll talk about that a little bit later. But again, you just need to know the fixed charges. You need to be able to memorize those or know what they are on the periodic table. So how do we name simple ionic compounds using metals with fixed charges? So again, MgCl2. Name the metal, and you're going to leave out the word ion. Remember, metals go first when we're naming. Magnesium. It says, remember to include Roman numerals for various variable charge metals. We'll talk about that later, so don't worry about that just yet. So again, name the metal, drop the ion or cation. So magnesium. Part 2. Name the nonmetal, changing its ending to IDE. Okay, so you wouldn't say chlorine, you would say chloride. And the reason why you say chloride is because those chlorine ions have a minus charge on it. So because they have a minus charge on it, we just, by naming rules, we're going to replace the ending with IDE. All right? So name of the cation or name of the metal, And then you're going to use the base name of the anion plus IDE. And then you're going to put it all together, and it's magnesium chloride. So again, that's pretty straightforward. We'll do lots of practice in a little bit, but these are naming simple ions with metals with fixed charges. Again, there are some metals that don't have fixed charges. Those are called variable charged metals, okay? Those are ones that have more than one possible charge. We distinguish these when naming by indicating their charge as a Roman numeral. For example, you can see on the slide that iron has two possible charges, +2 and +3. So when we're naming compounds, when we're writing out the name of an iron compound, you have to indicate the charge, because iron can be +3 or it can be +2. So you're going to indicate the charge by using the Roman numeral and then, or parentheses Roman numeral. So iron parentheses Roman numeral 2 is always iron +2. Iron Roman numeral 3 is always going to be iron +3. Copper's the same way. Okay, copper 1 and then copper 2. Lead 2 and lead 4, tin 2 and tin 4. Okay. I have iron and lead highlighted because those are the two variable charge metals that I'm going to want you guys to commit to memory. Okay. You're going to need to know that iron can either be a +2 or a +1, a +2 or a +3. You're also going to need to know that lead is a +2 or a +4. Right. There are many others. These are just some examples. You do not have to memorize the actual charges except for iron and lead, but you will need to understand when to use the Roman numerals. Okay, so we'll do lots of practice with that. So again, here's a little layout. Ionic compounds are a metal and a nonmetal, and there's two ways of naming them. You can name them to the left, where the metal forms only one type of ion, so that's just going to be the metal plus the nonmetal with an IDE. Then the other option are metals that form more than one type of ion. Those are the variable charge metals. So you're going to need to follow that arrow down. Name of the metal cation, Roman numeral in parentheses of the charge, and then the base name of the anion or nonmetal with an IDE. So let's do lots of examples. Okay, so let's say you have to write out the name for this iron oxide complex. Remember, iron is a variable charge metal. So what are the common charges? We said it was +2 and +3. So which one is this one? To find its charge, you're going to look at the non-metal, right? Because this is charge neutral complex, so because there's no charges indicated anywhere around it, that means we assume that the overall charge is neutral or 0. Since we already know that oxygen is always a -2, right, there can only be one possible scenario for this iron cation. It has to be iron 2, right? So we're going to write iron, parentheses, Roman numeral 2, and then we're going to write oxygen, but we have to change the name of the base, the ending of the anion to IDE. So it's going to be iron 2 oxide. Okay. And again, the Roman numeral 2 is because iron can either be a +2 or a +3, so I'm indicating that this is an iron +2 oxide when we write it out. All right, so let's just do some more examples, naming simple ionic compounds. So the first one, all right, we have calcium. All right, on the periodic table, that is not a variable charged metal, so we can just say calcium, and then we know that oxygen is the anion, and it's calcium oxide. We also know that we don't have to change this. I'm not asking you to change the subscripts on anything, right? You're not going to have to do that here when you're naming, when you're going from formula to name. You're going to take the formula that's given and then just name it. You're not going to have to change anything. The next one, NaCl, right? It's not a variable charged metal, so sodium. And then Cl is the anion, so you're going to have to add IDE, sodium chloride. The next one, copper. Turns out copper is a variable charged metal. Again, I told you you don't have to memorize this, but this is just practice. So we know that sulfide is always a what? If we look on the periodic table here, sulfur is always a 2 minus. So copper, this copper has to be a 2 plus. So it's copper 2 sulfide. Okay. You do need to know that copper is a variable charged metal, but you don't have to remember what the charges are. So you're always going to write copper 2 sulfide. Next one. So now we have Cu subscript 2, so 2 coppers and 1 sulfur. So what's that going to be? So again, that sulfur is always going to be a 2 minus. So since it's always a 2 minus, each copper is going to be a plus 1 because there's 2 of them. So that's going to be copper 1 sulfide. And then this next one, Al subscript 2, O3. We have aluminum. It's not a variable charged metal, so we don't have to indicate any parentheses. And then oxide, aluminum oxide. So when we're going from formula to name, it's pretty straightforward. The only thing that can trip you up is the variable charged metals. All right, so you're going to have to follow the steps for variable charged metals. But other than that, you just name the metal and then replace the ending of the anion with IDE. It gets a little bit different, a little bit more difficult when we are going from name to formula, which is what we're doing on this slide. Name to formula, okay? So the first one, mercury 2 chloride, all right? So again, mercury 2, the Roman numeral 2 indicates that there's a plus charge on mercury. Chlorides are always -1. So we have to sit there and say, all right, so if that one mercury atom is giving a +2 charge and one chloride anion is giving a -2, we're going to have to balance that out by saying 1 mercury for every 2 chlorides. So HgCl subscript 2. Potassium oxide. You're going to have to look at the periodic table. Where does potassium fall? It's in the first column. So it's a +1. Oxide, that's oxygen. It's always going to be a 2 minus, right? So it's going to be, you're going to have 2 potassiums for every 1 oxygen. K2O. Barium sulfide. Where's barium on the periodic table? It's in N equals 1, 2, 3, 4, 5, 6. Right? It's the 6th row, but it's the 2nd column, more importantly. So it's always going to be a +2. Sulfur, again, is always a 2 minus. So those are going to be 1 to 1. Barium sulfide looks like this because both charges are +2 and -2. They cancel out. Sodium nitride. Sodium is in the first column. It's going to be a +1. Nitride is a nonmetal. Left side, that's nitrogen. That's always going to be a 3 minus. So we're going to need 3 sodiums for every 1 nitride. So Na subscript 3, N. Chromium oxide. Chromium is a variable charged metal. You know that because I'm telling you with the Roman numerals. So chromium is, the charge on chromium is going to be +3. Okay, we got that from the Roman numeral. Oxygen is always a -2. So how are we going to do this? Well, we have each chromium atom is going to be +3. Each oxygen atom is going to be a -2. So what you're going to have to do is say, find a common denominator, right? So the common denominator here would be 6, right? So we're going to take 6. So if we want to get a +6 charge, we're going to have to multiply. We're going to have 2 chromium atoms will give us a +6. So how do we get -6 out of the oxides? Well, then we're going to have to take each oxygen and multiply it by 3. So Cr2O3, chromium oxide. Aluminum, +1, it's not a variable charge, +3, it's not a variable charge metal. So we have a +3. Oxides are always -2. Another way to do this to make sure everything balances. So since the charge is 2 on oxygen, -2 on oxygen, and +3 on aluminum, you can kind of swap out the subscripts where aluminum is going to be subscript 2 and oxygen is going to be subscript 3. Again, you just need to make sure the charge is balanced, okay? So I think we're going to stop right here. Yeah, so we're going to stop right here. That concludes the first portion of this lecture, okay? And then I will shortly upload the second portion of this lecture for us to talk about on Thursday.